So, directional derivatives. They're usually not too terrible to calculate. So let's talk about some, well, I'll just write the definition. So the directional derivative of the function f of xy at the point P, which we'll label as x naught, y naught, in the direction of, now the easier definition would be to say in the direction of the unit vector u, but you're not always going to be given a unit vector. So it's going to make more sense to say in the direction of any vector v, and then we'll talk about how to make it easier. So in the direction of the vector v is given by the following. We usually write it as d subscript v f, the derivative of f in the direction of v, and it's equal to the gradient of f, which is a vector, evaluated at the point P, dotted with the unit vector in the direction we want. So not the vector v itself, but the, excuse me, normalized vector v. V divided by its own magnitude. Most people will just say it's the gradient dotted with u and then say that u is the vector v divided by its own magnitude. So we can write it like this, or you can write it as duf equal to the gradient of f evaluated p dotted with u, where u is the vector v divided by its own magnitude. Either way you want to slice it. That's a p, by the way, so that's kind of terrible. So, long story short, if you're trying to find a directional derivative at a point in a certain direction, yes, you do have to have both of those pieces of information. You need the point of tangency, essentially, and the direction that you're trying to find the slope in, right? Because if you're on the side of a hill, it really matters which way you point to figure out what the slope is you're going to be traveling in. So then you find your gradient, you plug in your point, and then you find your direction, make it a unit vector, and you dot those two vectors together to get the overall slope. It might be positive, it might be negative, it might be zero. Those are the options. As a reminder, the gradient of f is just the vector of partial derivatives. So it's the partial derivative with respect to x, comma, the partial derivative with respect to y, for a function of x and y. I should mention, although it's not super important to our class, but I'm going to say it anyway. Gradient's kind of a larger concept. Like if you had a function of 3 variables, then the gradient would be the partial with respect to x, comma, the partial with respect to y, comma, the partial with respect to z, or whatever your third variable was. So it's always just the vector of partial derivatives in the appropriate order. Let's look at some examples. As always, if you have questions, ask them. The last time we were looking at our mountain example, which I still kind of wanted to run for a second here. Papers, come on, papers. Sorry, I'm terrible. So, last time we were dealing with a function f of x. Let's call this number 1. And let's let me put my, 1 second here. Do this. Let me pin myself. There we go. That way. Let me go that way. All right. Cool. So last time we were talking about the function f of xy equal to 9 minus x squared minus y squared. And I'm going to change up a little bit. Let's say we want to find the derivative of f at the point. Sure, we'll stick with 1, 2, 4 for the moment. In the direction of v equal to, let's make it not too terrible, 3, negative 4. So, relatively straightforward calculation. although it takes some practice. So first I'm going to find the gradient. The gradient is just going to be the partial with respect to x, comma the partial with respect to y, which in this case is not too bad. It's negative 2x, comma negative 2y. And then we're going to plug in the point. Now, I kind of gave us the point in a weird way. I gave the x, y, and z coordinate. We don't really need the z coordinate here. So my gradient evaluated at the point 1, comma 2, comma 4, I'm just plugging in 1 for x and 2 for y, and there's nowhere to plug in z, as there really shouldn't be. I'm going to get negative 2 times 1, comma negative 2 times 2. Okay. And then we're going to normalize our vector v. So we're going to say that the unit vector u is equal to the vector v divided by its own magnitude. And I picked a vector that has a nice easy magnitude for this example. The magnitude of v, I will just point out, is the square root of 3 squared plus negative 4 squared, which does end up equaling 5. Personally, I don't like to distribute the 5 or the 1/5 into the vector. You can write your vector as 3/5 comma negative 4/5. I would much rather write it as 1/5 times the vector 3 comma negative 4. So now when we find our directional derivative, and you should really write it like this because it's pretty standard. So you're going to write it as capital D subscript U F, like that. I'll remind you, this answer is not a vector. The answer we're going to get is just a number that's telling us about the slope. So if we do this, we're going to get, let's see. So these vectors dotted together, negative 2 comma negative 4, dotted with 1/5 times the vector 3 comma negative 4. I'm really kind of ignoring that 1/5. And I'm going to say I'm going to get 1/5 times the dot product, negative 2 times 3 plus negative 4 times negative 4. That's going to be 16 minus 6, which is 10. And 1/5 times 10 is 2. So what it's telling me is at that point on the surface, in the direction of the vector 3 comma negative 4, we're traveling upwards. And if we think about this graphically for a second, so yeah, I can think do I want to? Yeah, sure. So here's our little graph. Kind of like that. Oh, sorry, something's and then 1, 2, comma 4 is about right here. 1, 2. So about right there, like on the side of the mountain that's like towards you, right? Not the back side, but the front side. And what I'm saying is if we travel in the direction of x is positive 3, but y is negative 4. So we're traveling like forwards and left. We're going to be going up the hill, not down the hill. Not straight uphill, right? We're not going right towards the center like that. We're kind of going maybe like up around like that. Kind of in a sensible way, right? Where you wouldn't just try to go right up the hill, but around the hill kind of. So positive slope means we're going up, negative slope means we're going down. Let's ask some more questions. In fact, why don't you all try this next one? The same question, except now, part B, I want you to find the derivative, aka the slope of f. Now at the point, still 1 comma 2. I'll just write the 1 comma 2 this time. But now in the direction of v equal to negative 2 comma negative 3. It's not going to be quite as nice, but it's still going to be just fine. So try that. Gradient's the same. The directional derivative, the direction we're taking the derivative in is not the same. So you're gonna have to find the new unit vector u. I'll give you a minute to work on that. You guys can see that? You guys can see that okay? So pretty much the same type of calculation here. Our gradient of f evaluated the point 1 comma 2 is the same as it was before. It's still -2, -4. And our unit vector u is going to be the vector -2, -3 divided by the magnitude of that vector. What's the magnitude of the vector? Square root of what? Everyone's favorite lucky number, I think. Square root of what? I know at least one of you found the magnitude of this vector. Drum roll, please. The square root of -2. Thank you so much. Yeah, square root of 13. Cool. So now we're going to dot these together, and we're going to get our directional derivative. It's going to be -2, -4, dotted with, I'm going to put the 1/√13 on the other side just because I think it's convenient. So dotting these together, I get 4 plus 24. That's going to be 4 plus 24, right? 4, nope, not 24. I saw a 6 where there was a -3 instead. Sorry, 4 plus 12. Maybe you should write out your work, James. -2 times -2 plus -4 times -3. All that times 1/√13. Which is going to be 4 plus 12, 16/√13. Again, that's just telling us that in this direction of travel, the slope of the surface is positive, meaning we're traveling uphill, not downhill. And that really is the way I would encourage you to think of it, right? You're imagining this surface as some surface you could be walking along. And if your slope is positive, that means you're traveling uphill. If the slope is negative, you're traveling downhill. I know Davis is not a good place for that because we don't really have any hills in Davis, but you can imagine. So let's look at another example because not all of our functions are going to be quite so nice. Let's say we have now the following. We have the function f of x comma y equal to 5xy squared minus 4x squared y at the point 2 comma 1. We want to find, for a here, find the slope of f in the direction of v equal to, sure, 5 comma 12. Okay, same sort of deal here. So now our gradient's a little bit more complicated, but still not too terrible. So to find the gradient of f is going to be the partial of respect to x. So that's first going to be 5y squared minus 8xy, comma, the partial with respect to y. 5x times 2y, so 10xy minus 4x squared times 1. So there's our gradient at any point, but then we're going to plug in the specific point which is the point 2 comma 1. So the gradient of f evaluated at 2 comma 1 is going to be 5 times 1 squared, so 5 minus 8 times 2 times 1, comma 10 times 2 times 1, minus 4 times 2 squared. So it looks like we're getting a gradient of -11 comma +4. We're going to talk more about the gradient in a minute. The gradient is kind of important. Our directional derivative is going to be, let's just write it up here. So v is the vector 5 comma 12. Our unit vector u is going to be the vector 5 comma 12 divided by the magnitude of that, which is the square root of 5 squared plus 12 squared. You might recognize this as being another Pythagorean triple. 5 squared plus 12 squared is 169, and the square root of 169 is 13. This ends up being 1/13 times the vector 5 comma 12. So finding the directional derivative, we're going to get the directional derivative of f in the direction of u is these two vectors dotted together. So it's going to be -11 comma 4 dotted with 1/13 times 5 comma 12. And then I've said this a couple times, I'm gonna say it again. Those constant multiples, the 1/13th here, you can really kind of just ignore that until the end. I'm really just thinking of this as 1/13th times whatever the dot product ends up being. Negative 11 times 5 plus 4 times 12. That's negative 55 plus 48, which is negative 7. So we get negative 7 over 13. Okay. I want to point out how this question feels very similar to the next question, but is actually different. So, do I have enough room? I might have enough room. Yeah, probably. Let's not chance it though. So, here's part B. Find the slope of f in the direction of the point Q, which is going to be 5 comma 12. So I've tried to make this on purposely confusing. Purposely confusing. I don't know. I tried to make it confusing on purpose. So these two questions are asking something slightly different. The first one is saying, I'm telling you the way we're pointed. We're over 5 up 12. The second one, I'm not telling you the way we're pointed. I'm telling you the point we're pointed towards. So the difference here is that graphically, should pick smaller numbers. Oh, well. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Too many marks to make. So that's your vector v from the first part of this. Over 5 up 12. But they're not asking for that in the second problem. What they're actually asking for here is the vector that starts at the point we're taking the directional derivative at, which was, I'll remind you, 2 comma 1, and ending at the point 5 comma 12. So we're starting at 2, 1, and we're ending at the point 5 comma 12. That's a P there, that's a Q there. And those vectors are different, right? You can see they look different, right? They point in slightly different directions. So what we have to do here is say, well, great, our direction vector, our unit vector, our direction unit vector, I should say, is going to be the vector PQ divided by that vector's magnitude. So be really careful when you're reading these questions. Sometimes, most of the time, they'll give you like the direction you're finding the derivative in, but occasionally they'll say, we're finding the derivative in the direction pointing towards this point. And then before you start finding anything, you have to find the vector between those 2 points and then normalize it and then dot product things. So let's see what we've got here. So our PQ vector, we started at 1 comma 2. Sorry, 1 comma 2, nope, 2 comma 1. And we ended at 5 comma 12, so we went over 3 and up 11. So our vector PQ is the vector 3 comma 11. So then our unit vector is going to be 3 comma 11 divided by the magnitude of that, which is just the square root of 3 squared plus 11 squared, which I think is 130. So here we're getting 3 comma 11 times 1 over the square root of 130. Then we're going to dot that with our gradient vector, which hasn't changed, right? The gradient at this point, 2 comma 1, isn't any different because the slope we're going to get is going to be different because we're traveling in a different direction, but the gradient there is still the same thing. So our directional derivative now is going to be, I guess I'll write it this way, the direction and the PQ. I don't like writing it this way, but I did. So the derivative of f in the direction of PQ is going to be our previous gradient vector, which was negative 11 comma 4, dotted with the vector we just found, 3 comma 11 times 1 over root 130. Again, just for some notation here, I'll point out that that's our gradient of f, evaluated at 2 comma 1. That's our PQ divided by the magnitude of PQ. Dotting those together, we get negative 11 times 3 plus 4 times 11 divided by root 130, which is 11 over root 130. Not too bad. So directional derivatives are very computational, right? You find the thing, you find the other thing, you dot them together, you get an answer. That's kind of it. That said, let's see here. Sorry, just looking at one more example here. No, that's we could do other things. Sure, let's do one more before. So there's one more thing I want to say about that before we move along to still continue with this, but talking about something related. Yeah. Let's do one more example and then we'll say some other words. So let's say we wanted to do one more. We want to find the directional derivative of f of x comma y equal to y e to the negative x at the point 0 comma 4 in the direction of theta equal to 2 pi over 3. So we're going to do this the way I think of kind of the standard way, but then we'll talk about how we'll see something else as well. So we're going to use the usual things. We're going to find the gradient. So the gradient of f is equal to partial with respect to x, comma partial with respect to y. In that case, so the partial with respect to x is going to be y times the derivative of e to the negative x, which is going to be negative e to the negative x. So we're going to get negative y times e to the negative x, comma. I said y, I meant x. Sorry, let me say that again. The partial derivative with respect to x is going to be y times the derivative e to the negative x, which is negative e to the negative x. The partial with respect to y is going to be much easier. It's going to be 1 times e to the negative x. And if we plug in our point, it's going to be, let's see, we're going to get negative 4 times e to the 0, comma e to the 0, which is just going to be the vector negative 4 comma 1. Now, for our directional, or for the unit vector in the direction we're traveling in, we're just going to think of, well, there's actually an easy way to do this, I feel like, but let's talk about it. So my angle is 2 pi over 3, or it's 120 degrees. So we're kind of going in this direction here. And probably the easiest way to do this is just to say, well, if you want to find the vector that has a length of 1, you're just looking for the point on the unit circle. You're really just looking for the cosine and sine values. So really, I think the easiest way to say this is that my unit vector is going to be cosine of 2 pi over 3, comma sine of 2 pi over 3. Which in this case ends up being, let's see, cosine of 2 pi over 3 is negative 1/2. Sine of 2 pi over 3 is root 3 over 2. If you have questions about that, now is an excellent time to ask them. Another way to see this, if you like, is that our reference angle here would be 60 degrees, or pi over 3. If we drop this perpendicular, we've got a 30, 60, 90 right triangle. And the sides are, you can do it anyway, like I like to think of the sides as 1, 2, and root 3. And so I want the length to be 1, not 2, so I'm going to divide everything by 2. So really it's 2 over 2, root 3 over 2, and 1 over 2. But I went left, not right, so my x value is actually negative. I went up, so my y value is positive. Oh yeah, so the vector is over negative 1/2, up positive root 3 over 2. Just like we said. Sorry, I'm trying to think. Yeah, that seems fine. Oh, okay. Sorry, I'm just having a thought here about something I wanted to say, but that's actually not really true at all. So I'm not going to say that. Yes. I mean, yes, probably. I think so, but it might I mean, if your teacher might say more specifically what they expect you to be able to reproduce on the exam. But yeah, occasionally these angles do come up, so it's probably worth knowing. So then our directional derivative of f in the direction of u is going to be our gradient -4 comma 1 dotted with our vector, our unit vector -1/2 comma √3/2. Which is going to be, let's see, -4 times -1/2 is +2, and 1 times √3/2 is √3/2. And we can't really do much more than that, so we're going to leave it like that. Yeah. So let me ask you all. I wish I think of that. All right, we'll look. I'm just going to show you a picture here for a second, and then we'll talk about it a little bit. So yeah, I'm gonna have to remove this. So hopefully you're done looking at it because it's gone forever. I'll post the notes as I usually do. So let's say we were looking at this sort of, let me zoom in a little bit here. This kind of topographical map where these were the elevations, 100 feet, 200 feet, 300 feet, 400 feet. And I don't really care so much about this question that's being asked here. What I care about is really, I want you to think about if I were to say start, let's say right here. No, let's say right here. Sorry, I'm like, where do I really want to start? Let's say actually over here. What would be the path that would be the steepest? Or which way would it point? Towards 400. And what I really kind of want to say, and there's not really an easy way to say it, is the way we go up the incline the fastest is by crossing these level curves as quickly as possible. So we want to kind of minimize the distance we're traveling. So like we don't want to go like this way. That's not as fast as possible. I want to go that way, crossing this level curve kind of perpendicularly. Same deal. From here to here, I want to cross it, like I want to go as fast as possible. So what I actually am trying to say in kind of a roundabout way is when you're finding the direction that's going in the steepest possible way that you can, you're traveling in a direction that is always perpendicular to whatever level curves there are. Blanket statement. So, just want to say that again. On a surface, the direction of travel that is steepest, really I should say positively steepest, right? Because if you turn around, it would be the same amount of steepness, but you'd be going in a negative steepness kind of way. But I'll just is positively steepest. Crosses level curves perpendicularly or orthogonally. So we'll leave that out there, and we'll come back to that kind of a little bit. So let's talk about some properties of the gradient vector. And we'll come back, I promise. So properties. People usually just say the gradient, but I'm going to say the gradient vector so that we remind ourselves that the gradient is a vector. Okay, so let's remind ourselves of a few things. So this directional derivative, the derivative of f in the direction of u, we have been calculating as the gradient of f dotted with the direction vector u. And usually we've been calculating this in the normal way, right? Where we just like take the two vectors and then multiply the corresponding components together and add the results. But there's another way of calculating the gradient, which is that if you know the angle between the vectors, then you can say, well, that's going to be the magnitude of the first vector times the magnitude of the second vector times cosine of the angle between those two vectors. Where we're imagining like this is your gradient vector, and there's your unit vector, and there's the angle between them. Okay, so a couple questions. U is a unit vector. So what's the magnitude of U? Got to be 1, right? No other choice. Magnitude of U is 1 by definition. Okay, so this ends up equaling the magnitude of the gradient multiplied by, not dotted with, multiplied by cosine of the angle between the gradient vector and the unit vector. If I wanted to make this as large as possible, what's the biggest value that cosine can ever have? Think about the graph of cosine. How high does it go? 1. The biggest this can ever be is if cosine of theta is equal to 1. Or in other words, if the angle between the two vectors is equal to cosine of what angle equals 1? Yeah. But that means the vectors point in the same direction. So here's what we're saying. The directional derivative, which will equal the magnitude of the gradient, is the maximum value when the gradient and the vector u point in the same direction. Or in other words, the gradient is the direction of maximum steepness. Let me say it again. The gradient vector at any particular point is the direction where you have the steepest slope possible. So, yeah. So two things. Let's write this down on the next page. So, thing 1, the maximum directional derivative is going to be the following. The magnitude of the gradient times the magnitude of the unit vector times cosine of 0 degrees or 0 radians, same thing, which is going to equal the magnitude of the gradient. So if someone ever asks, what's the maximum slope you can have? It's just whatever the magnitude of the gradient is. I think the more interesting thing is that the maximum directional derivative occurs when the angle is equal to 0. Meaning, in the direction of the gradient. Right, because the unit vector we can pick to do whatever we want, right? We can pick to take the derivative in any direction we want in the whole kind of circle. But the gradient's already kind of set depending on whatever point we have. So whatever direction the gradient points in is the direction of maximal increase. If you couple that with the thing I started off saying a little bit a while ago, where the direction of travel to the steepest crosses level curves perpendicularly, what that means for us is that the gradient of a function always crosses the level curves in a perpendicular way. Let me show you an example, an easy example, one we've already kind of talked about. So we're going to go back to our example of f of x, y equal to 9 minus x squared minus y squared, which is a downward opening paraboloid. And let's just draw some level curves for a second. So I'll point out, if your shape looks like this, what kind of level curves am I going to have? I'm going to have the shape of circles. So if we draw a few of them, let me show you what I mean. So at the very top, at the point 0, 0, 9, when z is 0, I get a circle of radius 0. Not very exciting. But a little bit lower, when z is 8, well, if I plug in 8 here, I get 8 equal to 9 minus x squared minus y squared, or I get a circle of radius 1. Right? Because if 8 equals 9 minus x squared minus y squared, that becomes x squared plus y squared equal to 9 minus 8. So a little bit lower, circle of radius 1. That's when z equals 8. And then if we go a little bit lower down to say like z equal to 5, we get a circle of radius 2. So a little bit lower, z equals 5. And then finally, not finally, but finally for us, if we go down to say z equals 0, we're going to get a circle of radius 3. And then my circles don't look perfect, but I'm a human. You know. So z equals 0, z equals 5, z equals 8, z equals 9. So if we wanted to travel to a higher elevation as quickly as possible, we would do something like that. Okay, so I'm going to pick a point on, yeah, sure, I'm going to go with my skill standard. Let's pick the point. I'm trying to pick a point that's easy to deal with here. Let's pick the point. X is, sorry, I'm like trying to come up with something that's not the one I've just picked every time. But I guess I could pick x equal to 1 and y equal to 2. So if x is 1 and y is 2, we're going to be over here at the point right there. So there's the point where x is 1, y is 2, and z is 5. Now check this out. If we find the gradient at this point, and I'll point out again, we've gone over 1 and up 2, right? And the 5 doesn't really matter for this part. If we find the gradient at that point, well, the gradient in general is negative 2x, negative 2y. And if we plug in the point 1, 2, our gradient at 1, 2 is going to be negative 2, negative 4. Which exactly points directly towards the origin, which is exactly the direction of travel that's going to cross those level curves perpendicularly. So we're pointing exactly this way. And I've drawn it longer than I needed to, right? Because you don't really care about the length of the vector when you're drawing the direction. But that's the whole idea, is that that gradient vector is pointing you up the mountain in the steepest way possible. I might be emphasizing this a little bit more than necessary just because it was a hard thing for me to grasp my mind around when I was learning. I'm like, I kept coming back to like, why is the gradient again the direction that's pointing in the steepest direction? Because, okay, I guess that makes sense. If you ever forget why, it really comes back to the dot product. It's because the dot product is going to be as big as possible when these two vectors point in the same direction, which means the angle between them is 0. Okay, but the end result is that I'm trying to find the maximum value of the directional derivative. It is the value of the gradient's length. There's a better word for that. I can't think of it right now. And you're trying to find the direction. It's just the direction of the gradient. So now let's ask some interesting questions. Ooh, yeah, and we'll talk about something that's kind of terrible. Fine. So, question. What is the maximum rate of change, slope, derivative, whatever you want to call it, of the function f of xy equal to 3xy minus x squared at the point -1, 1, and in what direction does this occur? Okay, so we'll talk about the answer to the first part of the question. What is the maximum rate of change? The max rate of change is going to be the magnitude, that's the word I was looking for, of the gradient evaluated at the point -1, 1. Okay, my notation looks a little terrible there. Sorry about that. So let's find the gradient. The gradient is going to be the partial, so with respect to x will be 3y minus 2x, and with respect to y will be 3x. We plug in our point, which is -1, 1, and we're going to get 3 times 1 minus 2 times -1, comma 3 times -1, which ends up being 3 plus 2, so 5, comma -3. And the magnitude of the gradient is going to be the square root of 5 squared plus -3 squared, which is the square root of 34. And that is the answer to the first question. The maximum rate of change, aka the maximum steepness of the surface at the point -1, 1 is the square root of 34, or almost the slope of 6. So that means that from that point, -1, 1 on the surface, if you travel in the direction that is the steepest, it means that for every 1 unit you move in that direction, you're going to go up 6 units, which is very steep. Like hiking that would be terrible. Trying to think of what slope that would, like what angle that would be. It'd be a very steep angle, right? If your tangent function is equal to 6, the arctangent of 6 is steep. I don't know how steep, but steep. On the other hand, or I should say additionally, if we're asked the second question, there's a number of valid ways to answer the question. It really kind of depends on what someone is asking for. So if we're asking for the direction, well, the direction is just the direction of the gradient. So the direction, you can just say, well, the direction is going to be the vector 5, -3. That tells you which way to go. Now, the problem with that answer is that a multiple of it is also valid. You could say 10 -6 is pointing in the same direction, or 1, -3/5, or any non-zero multiple of this vector. Any positive multiple of this vector. If you did a negative multiple, technically you're pointing in the opposite direction. And the issue with that is people don't like having multiple possible answers when they're grading an assignment. Or if you were doing web work really doesn't love having multiple possible responses. So what they usually have you do, if they ask for the direction, is they almost always want you to give the direction vector as a unit vector. That might not be the case for your instructor, so you should definitely make sure you know what they want. But we could say the direction is that, or it might be more correct to say it's the gradient of f divided by its own magnitude, which in this case would be 5 over root 34, comma, -3 over root 34. Both of those vectors point in the same direction. I can't really say more than that, right? There's not just one of them, but only one of them is kind of uniform, right? This one, if I said, give me the direction vector that's a unit vector, we would all have to give the same answer. Whereas if I just said, give me a vector that points in that direction, there are multiple plausible answers, literally an infinite number, actually. So you should make sure you understand what your professor wants, because I don't know what. Um, yeah. Let's see. There's something else I want to say here. Oh, I know this. So, um, if on the other hand, so sometimes we ask a question like, oh, where'd it go? Well, let's see. I think it's over here. Apologies. I don't know. Let's not try to squeeze in another question in 2 minutes. Let's just we'll stop that. It's a good stopping place. We can stop there. On Friday we'll probably talk more about this, and then we might start talking about finding relative maxima and minima of surfaces. I think it's fun. Maybe even classifying them. All right.